Let's talk about store locators. This will make sense, I promise. You've probably used a website that has a store locator. For example, there's a chain of supermarkets in the UK called the Co-op. Like, what are they, the only cooperative? They have a monopoly on co-op or something? I don't know. On their website is a store locator. You can type in a postcode and it will list a selection of your closest co-op shops. Let's have a look at how this works. I'm going to open the Network tab in the Developer Tools and type a postcode. Unsurprisingly, the postcode is sent to some web server. Before I've even typed the whole thing, it's made an API request to get a list of possible postcodes that I might be interested in. When I select a postcode from the list, it then sends that to a different API endpoint. That one returns a list of shops that I might be interested in, which is then presented to me on the page. I also get a map view, which potentially has other problems, but I'm not super interested in that at the moment. The Co-op site uses Google Maps to provide this service. If you type your postcode into this page, then it sends that postcode to Google. You were never asked if you were happy for Google to know what postcodes you're interested in. We'll come back to this. Tesco offers the same thing. They use Mapbox APIs. Again, the postcode is sent to a different web server to the one that the main website came from. So your postcode searches are leaking beyond the one website that you're using. Plenty of other websites do exactly the same thing. B&Q is a chain of hardware and home improvement stores. They go a step further and guess your location based on your IP address. In most cases, this is going to be a good guess. They're probably using some API to do that too. But let's see what they do with a postcode. Looks like B&Q is using Woo's map, then making an API request to Kingfisher? What's Kingfisher? Ah, that's the company that runs B&Q along with similar stores under different brands. Huh. Screwfix and B&Q are actually the same company? I don't think I like that. Anyway, I'm drifting off topic. The point is that all these big chains are totally happy to ask you for your postcode and then send it off to some other web service you've maybe never heard of. Or worse, Google, and use that to locate your nearest stores for your convenience. There are companies that make money from buying and selling information like this person, who you can identify by this web tracking cookie, likely lives near this postcode. They build profiles of web users as they browse around many different websites, adding information to your profile as they learn new things. If all they did with this data was target adverts, then that might not be concerning. But maybe your life insurance company is buying that data and deciding that you've been looking up your nearest fast food chain a little too often. You're a greater heart attack risk than most. Looks like you're going to have to pay more for your life insurance. I'm not saying that they're all doing this, but when you consider that this is possible, it's better to prevent that data being collected in the first place. A little aside, this is why the EU created a law that forbids websites from placing tracking cookies in your browser without consent. Lots of website operators decided that the appropriate way to comply with this law was to put intrusive and confusing pop-ups on the page that make it easy to give consent and not always as easy to deny consent. But today's video is not really about that. There's lots of examples of websites that have these store locator features, but I've never seen one that is designed for privacy. I would love to come across a website with a store locator that verifiably did not let my postcode escape from my web browser into some random web service. This means that the postcode can't be allowed to get out of my web browser at all. So I guess I need to make that happen now. Let's talk about UK postcodes. There's currently almost 1.8 million active postcodes in the UK. Each one holds a small number of addresses. Sometimes a postcode has a single address inside it. Sometimes a postcode maps to an entire street with tens of addresses. Postcodes are deliberately constructed such that no house name or number is duplicated within a single postcode. This means that, technically, if you send a letter to 10 SW1A2AA, that will be delivered to the UK government headquarters. You don't need to write Downing Street on your letter, you don't need to write Westminster or London on it either. The postcode and door number is sufficient. It's still a good idea to include those details when you send a letter or package. They provide some redundancy. Every UK postcode is made up of two parts. The first part is called the outward code. The second part is the inward code. The inward code is the simplest part. It is always 3 characters long. The first of these is a digit, then the last 2 characters are letters. These tend to be allocated sequentially, but not with much consistency. They start at 0AA and continue with 0AB and onwards until 9ZZ. They aren't always all used. For example, for the outward code of AB12, the lowest currently active inward code is 3AA. There's some small gaps here and there until it reaches AB12 5YX, and then a sudden jump to AB12 9AL. The outward code is everything except the last 3 characters. This code can be 2, 3, or 4 characters long. For example, B1 is the 2 characters outward code for an area in the centre of Birmingham. B11 is a different area of Birmingham and is 3 characters long. We've already seen a 4-character outward code, SW1A. That Birmingham example is interesting though. It shows something that makes it tricky to parse a postcode. B11RS is a postcode for a shopping area in the centre of Birmingham. B111RS is a very similar postcode that is nearby, but it's in a residential area of Birmingham. If you write these without the space between the outward and inward codes, as many people often do, then they both start with B11. Any system that parses a postcode should therefore not assume that a postcode that starts with a known outward code is in fact located in that outward code. Instead, it should separate the inward code first, since that's always 3 characters long, and then pass what remains as an outward code. Okay, I think we understand enough to make something that works. So let's get into engineering a privacy-preserving store locator system. The way we're going to make this privacy-preserving is by avoiding sending any specific postcode over the internet to look up its coordinates. This means that we need the browser to do all the computation about the distance to each store from the postcode. Once the page is loaded, it should be possible to completely disconnect from the internet and still use the store locator. That means we need some way to know the GPS coordinates of every UK postcode without doing a lookup via a web service. The key thing that we need is a complete mapping of UK postcodes to GPS coordinates. There must be a database that contains these details. The Royal Mail should have a complete database of postcodes, right? After all, I can find any postcode with their postcode finder. We looked at 10 Downing Street before. Oh. None of these is in Westminster? What? Well, never mind that. I just want to know all the postcodes and their coordinates. Royal Mail does offer this information, and more. They can even tell you about all the addresses within each postcode in their postcode address file, or path. Can we get a copy of the path? Oh, we need a license. I suppose I would count as a micro-business, since I have 0 employees and turn over less than £2 million per year. Although they might consider me to be a solutions provider. If I'm one of them, then I have to pay thousands of pounds? The Royal Mail has monetized their postcode and address database. Who will save us from this terrible situation? Where is our saviour to provide freely available postcode information in a convenient-to-digest format? Drumroll please. The Office for National Statistics! That's right, the ONS provides a download that's updated every few months with all the UK postcodes and their GPS coordinates. If you thought I was going to say Ordnance Survey, well, haha, I didn't. OS does provide a similar dataset called CodePoint. In fact, the ONS dataset is actually based on the OS dataset, but the OS version doesn't include GPS coordinates. Instead, it provides UK National Grid coordinates. The National Grid is the grid system that OS uses on their maps, not to be confused with the National Grid, which is the UK's electricity distribution infrastructure. Am I off topic again? Maybe. Anyway, the conversion from National Grid coordinates to GPS coordinates is not required if I use the ONS dataset, so that's why I chose that one. I should clarify, the GPS coordinates are approximate. A postcode isn't really a single point, it's an area. It can be quite a big area. The Royal Mail even explicitly warns us about this on their website. Regardless, any point in that area is going to be a useful approximation for locating your nearest store. Alright, now we have a file that has all the data we want. All we need to do is write some JavaScript that fetches that file, ready to use offline, and when a user types in a postcode, it looks up the coordinates and then calculates the distance to each store. Easy! Haha, not so fast. This file is 1.4 gigabytes. That's enough to wipe out someone's entire mobile data allowance in a single page load. That's too big. Well, of course it is. It contains a lot of fields we don't care about. Let's get rid of all fields except for the postcode, longitude, and latitude. As we do that, we can also discard any postcodes that have been terminated, and any that don't have coordinates associated with them. I'm not sure what's going on with those, but they aren't useful. Okay, 48 megabytes. That's better, but it would still take about 5 seconds to download that over my home internet connection. It doesn't sound like a lot for one user, but I want this to scale well. I don't want to add a lot of additional load to the server, or consume excessive bandwidth. There's also energy to consider too. I think it's often overlooked, but coding for minimal energy usage is valuable. I think I can do much better than this. Let's take a closer look at how postcodes work. Earlier, I explained how a postcode is an outward code and an inward code. If I want to optimize how I store them, I'm going to need to think about them as data. The outward code always starts with a letter, the second character is either a letter or a number, the third might not exist at all, but if it does, then it is a letter or a number, the fourth also might not exist, but can be a letter or a number. To make parsing easier, you can always store postcodes in a fixed width format that is 7 characters long. You start with the outward code, you then add 0, 1 or 2 space characters as padding, and finally add the inward code. Given this pattern, the first character has 26 possible values, the second has 36, the third has 37 if using the space padding approach, the fourth has 37, the inward code's 3 characters have 10, 26 and 26 possible values respectively. I'm secretly teaching you information theory here. So the total number of possible postcodes is 26 times 36 times 37 times 37 times 10 times 26 times 26, which is about 8.6 billion. That's a super inconvenient number, actually. This means you can't quite store a postcode as a 32-bit integer. Even 33 bits is not enough. You need 34, but only just. So far, I haven't made any assumptions based on which postcodes are actually in use, and I want to keep it that way. 8.6 billion is the most postcodes we could have with this system. I want to avoid adding in any assumptions that reduce this space, so that this system continues to work in the future as more postcodes are added. We're going to have to get creative about how to represent postcodes. Let's ditch the CSV format and go for a raw binary representation. If I store each postcode as a number, then I can do that in 5 bytes. I need at least 34 bits, which is 40 bits if you round up to the next multiple of 8. 40 bits is 5 bytes, hence needing 5 bytes to store a postcode. Given that postcodes normally take up 7 bytes, this is a reduction of about 30%. While I'm doing that, I should also reduce the coordinates to a numerical representation too. Each one takes up about 9 characters in string form. A 64-bit floating point number would certainly be precise enough for a GPS coordinate. That costs 8 bytes. That's not a big saving over the 9 bytes they were before. Perhaps we could use 32-bit floats. That way we need 4 bytes per number. That's a lot better than 9. This is a reduction of 44%. Overall, including the commas and new lines and whatnot, the postcode and coordinates in string form in a CSV file took 28 bytes per entry. With a packed numerical representation, which does not need the commas and new lines, this is reduced to 13 bytes per entry. This is less than half the initial size. There's a much better way to do this though. Consider how a lookup works in this file. The user has typed in a postcode and wants to know if it is in the file. The search program needs to find that postcode in the file. The obvious simple algorithm to do this is to start at the beginning of the file, read the first postcode, see if it matches the typed postcode, and if not, move on to the next entry in the file. Eventually you will hit either the entry for the postcode you want, or the end of the file. Scanning the entire file like this takes a significant amount of time. For the CSV version, it's about 740 milliseconds on average for a successful lookup. Sometimes it takes longer, sometimes it's faster. It depends where in the file you find the postcode. Let's put a pin in that for the moment. Lookup time should be minimized. Another potential improvement we could make to the list of postcodes would be to reduce the amount of repetition in it. There's a lot of postcodes that start with AB right at the start of the file. What if I had some way to insert information into the file like postcodes from this point on start with AB, only the last 5 characters are stored. In that case I could remove the AB prefix and save a little space. Let's also put a pin in that idea too. Prefix repetition could be avoided. One last idea to explore. A postcode does not define a point. It defines an area. The coordinates provided for a postcode are an approximate center for the postcode area. Lossy compression is a category of compression where the data you get out of the decompression algorithm is not exactly the same as what you put into the compression algorithm. The decompressed value is an approximation of the original value. Sometimes this is unacceptable, like when compressing text, such as the subtitles on this video perhaps. Sometimes this is acceptable, such as when compressing a photograph. If each pixel is almost the same color as the original, you probably won't notice, nor will you care. In the case of our coordinates, the values are approximate anyway, so perhaps some lossy compression is okay. So here we have a few thoughts to guide the creation of a file format and algorithms for storing and looking up postcodes. Lookup time should be minimized, prefix repetition could be avoided, lossy compression of coordinates could be okay. With these things in mind, I designed the following. The file will contain details of the bounding box that encapsulates all UK postcodes. This can be represented with 4 numbers. It will then contain a table with an entry for each possible postcode prefix. Each entry has a value that is an offset into the rest of the file that indicates where to find the first postcode with that prefix. The rest of the file is then all the postcodes, encoded as numbers without their prefixes, followed by the coordinates expressed to a much smaller precision than normal, as a fraction of the length of the left and bottom edges of the bounding box. If that didn't make sense, don't worry. I'll walk you through the encoding algorithm and then the lookup algorithm, and it will all suddenly make sense when you see the lookup algorithm. As the encoder program reads the list of postcodes into memory and passes the coordinates for each one, it keeps track of the bounding box that surrounds all the postcodes. It's not actually a square, it's a part of the surface of a spheroid, but the maths we're doing doesn't actually care too much about the shape since it's just a transform that we are going to undo to get the original coordinates back later. It's just a pair of coordinates, we can visualize it as a square. So now we have longitude and latitude coordinates for the edges of our conceptual square as 64-bit floating point values. These values go directly into the file right at the start. Next, the encoder iterates over the postcodes, and for each one it splits the code into 2 parts. The first is the 2-character prefix, and second is everything else. Previously, I said that you need 34 bits to store the postcode as a number. With the prefix removed, that reduces dramatically to 24 bits. This is great because it fits very efficiently in 3 bytes. The coordinates are then compressed with a lossy compression scheme. This is the formula used to compress the latitude coordinate. The minimum latitude from the bounding box calculation is subtracted from the postcode's latitude coordinate. This calculates the distance into the box from the bottom edge. This is then divided by the height of the box. This results in a value in the range 0 to 1. This is then scaled up by multiplying by 65,535 and rounding to the nearest integer. This results in a 16-bit number that represents a latitude in the bounding box. The longitude is processed in a similar way, and now I can store the latitude and longitude in 4 bytes. This means that each postcode and coordinate entry is 7 bytes long, but doesn't have the prefix included. This is another good improvement over the 13 bytes per postcode from before, and it's only a quarter of the size of each entry in the CSV file. The encoder processes all the postcodes like this, and keeps a list of them. While it does this, it also keeps track of the prefixes in a table. The postcode table is sorted, so all the postcodes with the same 2-character prefix will appear together. As it scans the list, anytime a new prefix is encountered, it will put an entry in the table to indicate how many postcodes there were before the first one with that prefix. Once all the prefixes are added to the table, the total number of postcodes is added at the end of the table, and all of the prefixes that were not used also get values in the table. The value of each of these unused prefixes is the value of the next prefix after that one in the table. Now, the encoder writes the table values into the file, and then all the packed postcodes in order. And that's it, the file is ready to go. This file is about 12 megabytes. That's 25% of the minimized CSV file. But how do we use this file? Let's have a look at the lookup algorithm next. The first step of this algorithm is to make sure the postcode is correctly formatted. Some people will deliberately put a space in their postcode between the outward and inward codes. Some people will try to put such a space in and get it in the wrong place. Some people will use no spaces at all. Some people will use uppercase, others will use lowercase. Rather than require the user to type the postcode in the correct format, the algorithm just does this for them. Formatting a postcode is fairly easy. First, make sure all the letters are uppercase. Remove all the spaces that the user put in there, and then insert spaces between the outward and inward codes until you have a 7-character string. Since the inward code is always 3 characters, it's easy to find where to insert the spaces. Of course, some postcodes are too malformed to recover them. If you miss some of the code, or include an invalid character, this step will cause an error. Now we split the postcode up to get the 2-character prefix and the rest. we turn the prefix into a number and separately encode the rest of the postcode as a number, just like the encoder did when it created the file. Now we can parse the file. It starts with the bounding box coordinates, which are easy enough to read. Then we use the prefix number to look up where to start scanning for the postcode in question. Because of the way this part of the file was constructed, we can be sure that the next number in the table after this one represents the furthest we would ever need to scan to find a postcode with this prefix. So we make a note of that too. Now we multiply these numbers by 7, since that's the length of each postcode. And now we know the byte offsets into the file where we should start and stop scanning. Calculating the distance to the end of the table and adding the start offset allows us to know where to seek to, skipping lots of postcodes that have other prefixes. Now we just need to grab each postcode in sequence and compare it to the number we calculated at the start. If the postcode doesn't exist, then we will hit the end of the search range. If it does exist, then we will find a match and can then reverse the calculation done on the coordinates to compress them. The coordinates can't be retrieved exactly because there was some rounding involved in calculating them, and possibly some floating point errors too, but the results are typically within a few meters of the actual values. Certainly precise enough for something as approximate as a postcode. This lookup process is able to skip over lots of postcodes without even reading them. This makes it much faster than a lookup in the CSV file. The average lookup time is reduced from 740 milliseconds to only 3.3 milliseconds. This is a huge saving. 3/4 of a second is long enough to notice, but a few milliseconds is barely perceptible. This is certainly fast enough. Notice that this speedup is much more than you'd expect just from the file being shorter, so clearly the structure and lookup algorithm had a big impact too. Remember those 3 things from earlier? Lookup time should be minimized, prefix repetition could be avoided, lossy compression of coordinates could be okay. Designing with these in mind produced a much smaller and faster solution. But I'm not done yet. That lookup time is excellent. In fact, it's so good that I think it would be acceptable to trade off a little bit of lookup time for an even smaller file size. 12 megabytes is still a bit too big to expect a casual user to be okay with. So here's another thing to consider. The postcodes are sorted, and they come in densely packed clusters. There's big gaps between the clusters, but within each cluster it's easy to predict what postcode is going to come next. So perhaps some postcode in the file could just be replaced with a special value that means one more than the last one, and takes up less space than a full postcode. Similarly, the coordinates for adjacent postcodes can be quite close to each other, so these could be compressed further in a similar way. Let's give that a go. See how much space we can save. This encoding scheme is what I'm calling the delta encoding. Some of the values in the file are not stored in absolute numbers. They are instead stored as a delta on top of the previous value in the file. Previously, a postcode was a fixed 7-byte structure. Now it's going to vary in length. The postcode is normally 3 bytes, and the coordinates are normally 4 bytes. If the coordinates are close enough to the previous one, then I could instead store a pair of 8-bit signed integers that are added to the previous coordinates to get the next coordinates. The postcodes are sorted, so I never need to go backwards, so for the postcode delta I can store an unsigned number. I decided to limit this number to 6 bits, which will make sense soon, giving the delta a range of 1 to 64. Now the structure has 4 different formats. The first byte determines which format is used. Bits 7 and 6 of the first byte are flags that indicate which fields are delta encoded. If bit 7 is set, then the postcode is delta encoded. If bit 6 is set, then the coordinates are delta encoded. So the worst case scenario is when neither is delta encoded, the first byte just has the value 0, and then the next 7 bytes are the postcode and coordinates in the same format as before. This takes up 8 bytes, so it's actually slightly worse than before, but that's fine because the next 3 cases are far more common. If the postcode is delta encoded, then the delta to the next postcode is stored in the last 6 bits of the first byte. The coordinates then appear immediately after this. If the coordinates are not delta encoded, then this case is only 5 bytes in total. Perhaps only the coordinates are delta encoded, in which case it's 6 bytes in total. Finally, the best case is when both of them are delta encoded. For this case, I only need 3 bytes to store the entire entry. It turns out that 91.9% of all the postcodes can be encoded in the 3-byte format, and only about 0.37% of them need to be stored in the fully expanded format. This saves a lot of space. The new data file is only 5.5 megabytes. This encoding scheme is much more complicated, and so the lookup time does suffer a little bit. The lookup algorithm needs to be modified to handle the delta encoding. It needs to keep track of the previous postcode and coordinates as it scans the file. It needs to parse the structure to figure out how to update its internal state and to know how far to move the cursor onwards. Previously, it was always moving by 7 bytes. Now it might be 3, 5, 6, or 8. So how big is the effect? Well, the average lookup time with this method is about 6.6 milliseconds. Despite the file being less than half the size it was before, the lookup time has doubled. That's unfortunate, but it's still really fast. It's still in the barely perceptible range. Looking at the graph, we can see that both of these formats handily beat the CSV format. Getting speed gains has been much easier than getting space gains, but I'm happy with the delta encoding scheme's size and speed. So, getting back to the problem I wanted to solve, let's have a look at a little demo that uses this system to do a privacy-preserving locator tool. We're back in Firefox with the Developer Tools window open. I've cleared everything from the Network Requests tab after loading the page. The search tool is not enabled yet. Since it needs to download a file that is slightly abnormally big for a website, I thought it best to make sure the user is aware that they're about to download it. Clicking the button, you can see that the file download shows up in the Network Requests tab. And now the search tool is enabled. At this point, I could totally disconnect from the internet, and this would still work. I type in a postcode, press search, and now I get a list of all the Automobile Association call boxes sorted by their distance to me. Notice that no additional network requests were made. The lookup happened offline. In a real-world scenario, I might expect one additional network request to occur when the search tool loads, to load the list of locations, but that can also happen before the user ever types a postcode and still preserve privacy and allow offline use. I'm just a small YouTuber with zero clout, so I'm not really expecting any big corporation's website to start using this anytime soon, but if you happen to be someone who makes technical decisions for such a website, I would love to be able to say I've convinced you to switch to this approach. I've only just finished making this work in my demo, so there's some practical considerations that I still need to figure out for large-scale deployments. If you have useful ideas or feedback regarding that, then please let me know by submitting an issue on the repo linked in the description. There's also a link in the video description to find the live demo. Before I go, I want to leave you with some thoughts about privacy and technology. Big tech companies that provide web-based services have big incentives to sell your personal data. This isn't something that is inherent in technology. I hope that what I've shown today has demonstrated that effectively. Technology can be applied in ways that preserve privacy if the people creating that technology endeavor to make it that way. Big tech companies generally don't do that. I hope I've also demonstrated that it's worth being frugal with energy and data. Spending that extra effort to minimize the size of a file means that the file can be delivered much quicker and with less energy. Spending the time to minimize the computation required to process it also reduces the energy used. Sometimes it's a small effect, but it could multiply up to something much bigger. Maybe I've inspired some of you to apply a similar ethos to the way you write code. That'd be nice. Please leave a kind comment, gently pet the like button an odd number of times, and if you want to stick around, press subscribe. Thanks.